Hi everyone, this is Yuchen, Zhang, and Li. Today our topic is locality-sensitive hashing for minhashing. Finding similar documents is a very common task we perform. For example, finding plagiarism and finding mirror pages. Mirror pages are the web pages who have similar contents. Eliminating similar pages is commonly used when search engine tries to show search results, for users do not want to see many similar results. Checking documents one by one, bit by bit, is time-consuming. It needs a running time of big O of n squared times d. N refers to number of documents, and d refers to the average length of documents. We have a quicker way to complete this task with some special algorithm. This algorithm is called locality-sensitive hashing. Before I talk about locality-sensitive hashing, I want to talk about some concepts of similarity. We say two documents share more common pieces are similar. This is a chapter level similar, not meaning. How do we quantify the idea of similarity? We use an index called jacket similarity. This jacket similarity is easy. It is computed by the intersection of two sides over union. In the picture, the jacket similarity is 3 over 8. In all of those questions above, similar documents are documents who share common pieces of strings. Now let's talk about the locality-sensitive hashing algorithm. A general flow of this algorithm is shown in the slide. For those documents who share many common pieces that are identified as similar, before we check the similarity, we can divide documents into shingles, and then we can associate with each document the set of k shingles that appear one or more times within that document. The set of strings may cannot be manipulated as efficient as a set of numbers, so we use an algorithm called minhash to represent the shingle set with numbers without losing the similarity of sites. At last, we perform locality-sensitive hashing of the signatures and find candidate-similar documents, which we may call them candidate pairs. I and my teammate would introduce those steps one by one. First, let's talk about K shingles. Shingles are many pieces of substring of the documents. We may want to define the length of shingles as K. For example, if the document is ABCD, ABD, then the two shingles are AB, BC, CD, DA, and BD. K should be picked large enough that the probability of any given shingle appearing in any given document is low. For example, if our corpus of documents is emails, picking K equals 5 should be fine. Instead of using substrings directly as shingles, we can pick a hash function that maps strings to length k to some numbers of buckets and treat the resulting bucket number as a shingle. The set representing a document is then the set of integers that are bucket numbers of one or more k shingles that appear in the document. In this way, not only has the data been compacted, but we can now manipulate shingles by single-word machine operations. Set of shingles are large. Even if hash them from string to numbers, the space needed to store a site is still roughly 4 times the space taken by the document. If we have millions of documents, it might be while not be possible to store all the shingle sites in the main memory. We want something, first, can represent the shingle site. Secondly, can be used to estimate similarity of two shingle sites. And thirdly, it only takes small space. So how do we do this? Our answer in the slide is to replace large sites by much smaller representation called signatures. The important property we need for signature is that we can compare the signature of two sites and estimate the jacket similarity of the underlying sites from the signatures alone. It is not possible that the signatures give the exact similarity of the sites they represent, but estimate they provide a close, and the larger the signatures, the more accurate the estimates. Before explaining how it is possible to construct small signatures from large sites, it is helpful to visualize the collection of sites as their characteristic matrix. The columns of matrix correspond to the sites, and the rows correspond to the elements of the universal site from which elements of the sites are drawn. There is a 1 in row R and the column C if the elements for the row R is the number of the sides of column C. Otherwise, the value in position RC is 0. The signature we desire to construct for sites are composed of the results for a large number of calculations, say several hundred, each of which is a minhash of the characteristic matrix. To minhash a site represented by a column of the characteristic matrix, pick a permutation of the rows. The minhash value of any column is the number of the first row in the permuted order in which the columns has a 1. Although it is not physically possible to permute very large characteristic matrices, the minhash function h implicitly reorders the rows of the reordered matrix. In the permuted matrix, we can read off the values of h by scanning from the top until we come to a 1. Thus, we see that h1 that the hash value of site 1 is A, and the hash value of site 2 is C. Hash value of site 3 is B, and hash value of site 4 is A. There is a remarkable connection between minhashing and the jacket similarity of the sites that we minhashed. The probability that the minhash function for a random permutation of the rows produces the same value for the two sites equals the jacket similarity of those two sites. To see why, we need to picture the columns for those two sites. Taking two random sites as an example, the rows can be divided into three classes. First, type X rows have 1 in both columns. Second, type Y rows have 1 in one of the columns and 0 in the other. Thirdly, type Z rows have 0 in both columns. Since the matrix is sparse, most rows are of type Z. However, it is the ratio of the numbers of type X and type Y rows that determine both similarity between set 1 and set 2 and the probability that the hash value of set 1 equals to the hash value of set 2. Let there be X rows of type X and Y rows of type Y. Then the similarity of X of set 1 and set 2 is X over X plus Y. The reason is that X is the size of the intersection of S1 and of set 1 and set 2, and X plus 1 is the size of set 1 set 2 union. Now consider the probability that the hash value of set 1 equals to the hash value of set 2. If we imagine the rows permuted randomly and we proceed from the top, the probability that we shall meet a type X row before we meet a type Y row is X over X plus Y. So we can see that the jacket similarity of two sites is exactly of the probability of the hash value of set 1 equals to the hash value of set 2. We can represent our characteristic matrix more precisely with more signatures. Again, think of a collection of sites represented by their characteristic matrix. To represent the site, we pick a random number k of permutations of the rows of characteristic matrix. Perhaps 100 permutations or several hundred permutations will do. Call the min-hash function determined by these permutations h1, h2, until hk. From the column representing site S, construct a min-hash signature for S. The vector hash value of S, the first hash value of S, the second hash value of S, and then the case hash value of S. We normally represent the list of hash value as a column. Thus, we can form from the characteristic matrix a signature matrix, in which that the ith column of characteristic matrix is replaced by the min-hash signature vector for the corresponding column. Note that the signature matrix has the same number of columns as the characteristic matrix, but only n rows. Even if the characteristic matrix is not represented explicitly, but in some compressed form suitable for a sparse matrix, it is normal for the signature matrix to be much smaller than the characteristic matrix.
It is not feasible to permute a large characteristic matrix explicitly. Even picking a random permutation of millions or billions of rows is time-consuming, and the necessary sorting of the rows would take even more time. Thus, permuted matrix, like we mentioned before, is conceptually appealing, but it is not implementable. Fortunately, it is possible to simulate the effect of a random permutation by a random hash function that maps row numbers to buckets. A hash function that maps integers 0 through k minus 1 and to buckets numbers 0 through k minus 1. So we can maintain the fiction that our hash function h permutes row R to position HR and in the permuted order to simulate the precise of random rows. For example, V has 4 sides and the representation matrix. Then we randomly choose two hash functions h1 and h2. The x is the row index. We first compute the hash value from row 0 to row 4. Then initial signature table. All signature values is infinity. Then we update the signature row by row. For the row 0, the hash value is 1 and 1, and only S1 and S2, S4 has element at this row, so we can update S1 and S4 signature value. 1 less than infinity, so after process the row 0, the signature table is shown as the table at the bottom right. We do the same manipulation on row 1, and the hash value is 2 and 4. Only as S3 has element at this row, we can only update S3's signature table. Cause both 2 and 4 are less than infinity, we can update it. The result is shown as bottom right. We do the same manipulate on row 2 and the updated signature is shown. Process the row 3. Process the row 4. We get the final signature table shown at the bottom right. From the signature, we can see S1 and S4 signature are similar or same, which means S1 and S4 are similar. And S2 and S4 signature are totally different. S2 and S4 are different in actual. We implement this min-hash algorithm and get the experiment result. There are 6 sets and we randomly choose 4 hash functions and get the min hash signature. The score is the similarity between first file size and the last set. The result is also makes sense. Even though we can use min-hashing to compress large documents into small signatures and preserve the expected similarity of any pair of documents, it still may be impossible to find the pairs with greatest similarity efficiently. The reason is that using the min-hashing signature to find the similarity documents, the running time is still big O of n squared k. N is the number of documents and k is the length of min-hash signature for each document. One solution is the use of locality-sensitive hashing to hash the similar document to same bucket and only compare the documents in same bucket. We divide the min-hash signature matrix into B bands consisting of R rows each. For each band, there is a hash function that takes vectors of R integers and hashes them to some large number of buckets. Columns are agreed in any band will be treated as a candidate pair. Check each candidate pair whether they are similar. This is an example. We divided the min-hash signatures into 4 bands and each band there are 3 rows. Randomly select a hash function for each band. The result is shown as above. The red box has pointed 2 sides which they are hashed into one bucket in band 1, which means these 2 sets are a candidate similar pair, which can be checked similarity in following steps, no matter whether they are agree in other bands. Now we can analyze the banding technique. Use B bands of R rows. The probability of signatures of 2 sides agree in one row is S, is J-car similarity, and the probability that the signatures agree in all rows of one particular band is S power of R. The probability that the signatures disagree in at least one row of a particular band is 1 minus S power of R. And the probability that the signatures disagree in at least one row of each of the bands is 1 minus S power of R and power of B. So the probability that the signatures agree in all rows of at least one band is 1 minus S power of R and the power of B. Therefore, they can be a candidate pair. And this graph shows the relation between similarity and the candidate probability. The x-axis is the J-car similarity of documents, which is S, and the y-axis is the probability of becoming a candidate. The threshold, this is the value of similarity S at which the probability that is the value of similarity at which the probability of becoming a candidate is 1/2. It is a function of B and R. The threshold is roughly where the rise is steepest, and for large B and R, we find that pairs with similarity above the threshold are very likely to become candidates, while those below the threshold are unlikely to become candidates, exactly the situation we want. And now we can to overlook the algorithm. We want to find the similar documents. We need to singulate the document and then to do minhashing to get the signature of each document. And we can use the LSH algorithm on the signature to get the similar candidate pairs, and then we can check whether the pair are similar to get the similar documents. This is our reference and the implementation code link. And that's all. Thank you.